This is an introductory video where I'll discuss some very basic definitions and discuss a lot of applications of optimal control. So what is optimal control? Let's look at that. Without using any math, I could define optimal control as a set of techniques to obtain the best performance out of a process. So there are two phrases which are peculiarly phrased here. What is the best performance and a process? So we'll define them a little bit more carefully, but optimal control essentially consists of conditions, mathematical conditions under which such best performance might be achieved, and some analytical and numerical techniques so that we could figure out how exactly to get the best out of a process. So what is a process? A process, for the sake of this course, is any entity that evolves over time. And I've put a little asterisk there next to time because sometimes the variable that we call as time might actually represent something else. We'll come across a few examples as we go along, but let's not worry about it so much. And of course, we need to assume that this process, whatever it might be, needs to be controlled, and there are some mechanisms by which we can control it. Otherwise, there is nothing to talk about. But what do we mean by best performance? Well, that's really up to the user, and in different cases, we'll have different definitions of what we mean by best performance. So, for example, we might want a car to go as fast as possible. We might want a path to be as short as possible. We might want a process to be operated in as cheap a way as possible, and so on and so forth. And we'll look at some of the more standard definitions of all of these things, but it's really up to the user. Okay, and talking of the user, let's look at a bunch of application examples. Now, the purpose of these examples is, one, to give you an idea of the broad range of topics that can be addressed by optimal control techniques, and two, some of these problems are problems that we'll actually come back to and look at more carefully when we learn about some of the techniques used in optimal control. Okay, so let's look at this first example, what's known as the Queen-Dido problem, or also known as the isoperimetric problem. So legend has it that Queen Dido, who was apparently the first queen of Carthage, which is now modern-day Tunisia, she was in exile, and she landed up in a portion of northern Africa, and she met a local tribesman who said that she could have as much land as possible, but the condition was that she had to cover all that land with an ox hide, as in the skin of, well, presumably dead ox. Now, Queen Dido was very smart, which is why we still talk about her, and she decided to cut up the ox hide into a bunch of very thin strips, and she made a rope out of it, and she encircled a very large piece of land, which is apparently morphed into what is modern-day Tunisia. So the question, the optimal control question, is what should be the nature of this curve that encircles a maximum amount of land? So what is the shape of the rope that encloses a maximum amount of area? And the answer, I'll give you the answer right now. It's a circle, but there are ways to prove it. Okay, so that's one application of optimal control. Determine the shape of a curve that encloses the maximum amount of area. Now, as you see in this video, here's another application of optimal control. Boats have a hard time when they're navigating in strong currents, and the direction of the current plays a very significant role in how much energy the boat spends and how much time the boat spends from getting from one place to the other. So if you look at the static map now, that essentially shows you, for example, currents or maybe wind conditions if you're talking about an aircraft, but the nature of the problem remains the same. So if you have these strong currents in a body of water, for example, what is the fastest route for a ship to navigate from one point to the other? So this is actually a problem that we'll talk about in a lot more detail, and in some cases it does have an analytical solution. So this is called the Zermelo navigation problem. We'll come. The Zermelo navigation problem is an example of a problem where you want to move your system from the current condition, so the current position the boat is at right now, to a desired position. So you want to go from one point to the other. Now this example that you see on the screen, chemical process regulation, this is an example of optimal control application where you want to keep the system at its current state. So you want to regulate something to maintain a certain condition. So for example, you might want to maintain a preset production rate where you have, let's say, disturbances coming from the environment, disturbances from the input, and so on and so forth. You would like to minimize the deviation from a preset rate of production, but you'd also maybe want to spend a minimum amount of energy while doing so, because let's say in this particular example, energy is spent to produce another source of energy. So obviously, to remain profitable, you want to spend the minimum amount of energy to maintain the preset production rate. So there is another optimal control technique that enables you to do such a thing. It's called linear quadratic regulator, and we'll study that in quite a bit of detail. Now, when we talk about aircraft guidance, both kinds of problems show up. So in one case, you might want to find a path or a trajectory between 2 points that is in some sense the best way to go from one point to the other. So that's an example that is very similar to the Zermelo problem. But you might also want to maintain certain conditions. So for example, you might want to maintain altitude, or you might want to maintain tracking of a target, as you see in this video. And these kinds of problems are now becoming very, very important with the advent of unmanned aerial vehicles. And that's something that's very close to my own research area, and this is something that we'll have a lot of examples to discuss in the course. So I talked about finding best paths for aircraft to go from one point to the other, but this is probably a little bit more clear in terms of racing. So this is an example. The video that you see right now is Fernando Alonso riding a Formula One car around the British Silverstone circuit, and I believe this video is where he sets the world record fastest lap around this particular circuit. So in this case, the performance is very well defined. You want to go as fast as possible. And as you can see in this video, there are enormous speed variations, and one might question what is the best way to vary speed along different points along the circuit so that you can go as fast as possible. So when do you accelerate, when do you brake, and so on and so forth. And as you can see, the driver, Fernando Alonso in this case, has determined this from a lot of practice and from experience, but possibly there's an analytical way to find this out. So we will actually come to this problem as well during this course. Similar similar guidance type of a problem. So let's say you have a fighter aircraft that is in enemy territory and wants to go from one point to the other, but there are people who don't want the aircraft to do that and would like to shoot it down. So that's a threat that the aircraft has to navigate and try to minimize its exposure to threat. So sometimes you may be able to quantify this kind of threat in terms of a field. You may want to quantify that as a intensity map, for example, kind of like a elevation map. And you may want to say, I want to go along paths with where the total amount of threat that I get exposed to is the minimum. And optimal control will allow us to determine these kind of paths. Now, here is an example where the process that evolves is not as a function of time. So this is where that asterisk back in this definition slide comes into play. So here I'd like to find a surface which gives me which is a minimum drag surface. So if I take this two-dimensional picture and rotate it around that dotted line, I will get a three-dimensional surface, and I would like that surface to have minimum drag. Now here, what is of interest, the process that is of interest, is the curve, the black curve that you see, and it is a function of position. So here the independent variable is position, not time, position along the dotted line. So we'd like to find the function that defines this curve, and that's something that also has an analytical solution in this specific case. Finally, similar kind of a problem. So you're talking of minimum drag. You may also want to minimize heat. So this is a problem that has actually been solved with optimal control. When you want to have a spacecraft re-entering the atmosphere, you'd want it's going to experience atmospheric drag and the surface is going to heat up, but you'd like to, for example, minimize the amount of heat that that the drag generates, and this leads to another kind of optimal control problem. People have looked at this kind of problem and found the minimum heating trajectories. My last example has nothing to do with engineering. Let's say you're an investment banker with a lot of money to invest, and let's say you want to buy either stocks or bonds or real estate or maybe a combination of all these things with the objective of, well, obviously maximizing profit over a certain time horizon. Now, the reason this is an optimal control problem is because you could change your investments and you could change your portfolio. So that's what makes this a process that evolves over time. And we'll study a technique called dynamic programming, which if you have some knowledge of the risks associated with those stocks or bonds and so on, you could have a policy that will allow you to invest while maximizing profit. So we've seen a multitude of examples, and as the course goes along, we'll tackle some of these. But really, what you should take home from this discussion is a very wide range of problems that can be addressed with optimal control. And one thing that you should appreciate is to be able to address this wide range of problems. So they come from different engineering disciplines. One of them is not even an engineering problem. To be able to address such a wide range of topics, the only way we can do that is to have a very strong abstract mathematical framework. So we're going to spend a lot of time in this course doing math, but I want you to be very clear about why we should deal in such abstract terms and not just focus on one particular problem. The answer is that the payoff is very high. So once you learn how to work with the abstract math and then map that abstract math back to real world problems, then you have a small set of tools that can be applied to a very large set of real world problems.